So I want to introduce somebody who's doing heavy research. Like they're really on the ML research side. This speaker, to give some context, has a PhD in computer science from McGill. They're also from bachelor's and master's Carnegie Mellon. Shout out to CMU. Woo! They have extensive research history in reinforcement learning and NLP. They have, for researchers in the crowd, they have thousands of citations. Now, I've published papers, and I have 100 times less citations than this. So being published is not the same as having thousands of citations. It's not like TikTok views. It's like actually a big deal when people cite your research. And so I don't know, that stood out. They also worked with Google Brain and I believe Microsoft. And now they're starting a company called Manifest AI, and they're building a neural network to model all human output. Really interesting. So let's hear more from Jacob Buckman, CEO, Manifest AI.
Thanks, Gail. All right. Thanks so much for having me. I'm here today to talk to you about context, which of course refers to the amount of tokens typically that can be fed as input to a LLM all at once and be synthesized all together, and about how context is the next frontier, and by this I mean the next frontier of scale. We've scaled up the parameters quite substantially. We've scaled up the data sets to encompass the entire internet, and what's happening next is we'll be scaling up the context, the amount of input that the LLM can ingest altogether. The benefits of this are manifold and oft talked about, so I'm not going to go too much into them. In-context learning of entire data sets. No more fine-tuning. Just throw it all into the context and let the network figure out what's going on. Agents who don't have to be reminded of what task they were doing every couple thousand tokens, but can actually take multiple attempts at a task, learn from their mistakes, and improve by repeated attempts. Chain of thought, and most interestingly for this crowd, I believe is the beginning of a transition from centralized to decentralized AI, but we'll come back to that point later. This is going to be a research-themed talk, no math, but a lot of sort of first principles, conceptual discussion, trying to build up to the important ideas. So we'll start off with a very simple pictorial diagram of a large language model, some input, which is usually some natural language prefix, and it predicts a distribution over the next tokens. Now, if you were to write this as an equation, it might look something like this. NN theta, where theta is the parameters, give it a context, gives you back a response. I'm actually going to bring the parameters into the argument list here, now make it a pure function from parameters and context to a response. Up to here, probably familiar to everybody. I'm going to make one further change, which might be surprising. I'm going to write it instead as a function from parameters and a state to a response. If you're an OG and worked on RNNs back in the day, you'd be like, oh yeah, state, that makes sense. For transformers, it's not as obvious that you can use a state, so I'm just going to do a quick detour into a little perspective on why you can actually interpret a transformer as a recurrent neural network, meaning something that has a state. So again, you usually think of it as a mapping from a bunch of inputs to an output. But when you look at the actual way that a transformer is used during an autoregressive unrolling, like in a language modeling application, you see it's actually looking at a prefix, and then a larger prefix, and then a larger prefix. And what this means is that each of these prefixes constitutes a piece of data which maintains the entire information that the neural network is using to predict up to this point. In other words, a state. So written as a RNN, you see that the process of a transformer unrolling is still the exact same mathematical structure as an RNN unrolling, but uses a growing state. And in fact, this is a state that you're familiar with if you've ever done any inference. It's the KV cache. So you can view the KV cache as the state of a transformer, and therefore the transformer as a whole as a special recurrent neural network with a growing state. So going back to this, parameters and state are each just going to be a matrix, right? They're just a bunch of numbers that encode some particular thing about the behavior of the neural network. If you want to get a good response, then you better have a good state, and you better have some good parameters. How do we pick those numbers? For parameters, we're all very familiar with the process that we lovingly call training, right? You take a data set and you essentially apply compute to it. I'm obviously abstracting a lot here. And the output is this list of numbers that gives you sort of the brain of the neural network. What about for the state? Now, this is the interesting part about writing it this way, is there's actually a nice symmetry here. To create the state of a transformer, that is, the information going into the next prediction, we do inference. we start off with some data, which we call the context in this case, not the data set. We pass it through some compute, and what comes out is a list of numbers that encode what the neural network is going to do next. Now, looking at this picture, you see a nice, clean symmetry. I'm going to write it like this to make it look even more clean and even more symmetric. And now, I want to go and think about what each of these objects are. Ultimately, they're all just going to be pieces of data living on a hard drive or RAM or something. And let's think about the sizes of each of these objects. For reference, I'm going to be using numbers from Llama 3.1, the 400 billion parameter version. I expect the conclusions that I'm going to draw from this to be generic across pretty much all hyperscaler foundation models, most of which end up following the same scaling laws, so coming out pretty similar. Parameters, 400 billion parameters is 1.6 terabytes of information just to store this model, to store the weights. The data set was actually 30 terabytes. This comes from summing up the size of all the data points shown to the neural network. The state, 60 gigabytes. This is the KV cache when it's completely full at the maximum context length of Llama 3.1. Anyone want to guess what the size of the context is in bytes to keep them all comparable? It's 256 kilobytes. Kilobytes. This is 9 orders of magnitude off from everything else. And I think, looking at this picture, almost no further argument is necessary, right? Obviously, we're going to be scaling the context next. And in fact, this is actually even a little bit misleading. 256, it's kind of too large. Anyone who's played with the most recent generation of models probably has some feedback along the lines of, if you really try to fill up the whole context, it can't use it nearly as well. It starts forgetting information and being confused as compared to just giving it a smaller amount of information at once. And that's because this requires a little bit more reverse engineering, actually figure out where the training tokens came from. 95% of training tokens came at a context length of 8K. And only at the very end of training, token-wise, did we start seeing longer and longer context until the final little bit of training was at 128K. It's enough to make it not go completely haywire when you give it that many tokens, but not enough to get the same real goodness of performance that you get in the 8K range where most of the training actually happened. So going back at this, right, it's a bit ridiculous that we have 2 ways of giving data to the model to govern the response we're going to get out of it, and we're putting 1 billion times more data into one of them. Why would we be doing that? Is it because we don't get benefit from putting data into the state? No, we get very concrete and well-understood benefits. This is what you call a context scaling curve, or context-wise loss curve. It basically shows that as you give the model more and more tokens of context, its predictions improve. In this case, just measuring the negative log likelihood, the loss, and meaningfully, right? The gap between these 2 lines, which are models at very different scales, is not as large as the gap between the end of one line, when you're giving it a lot of context, and the beginning of that same line. So if it provides this concrete benefit, why are we not exploiting that? Well, of course, the benefit comes for a cost. The attention layer is typically, by far, the most expensive part of the neural network computation at long context. It grows quadratically, where all the rest of the costs grow linearly, so it quickly comes to dominate. And ultimately, as much as we would like to be training with long context, the decisions have been made for us by physics. There's some optimal context length for any given training setup, and you have to weigh it on the scales of GPU justice. In some sense, if you're a hyperscaler, it's almost like a deal with the devil. You've obtained power, but given up some of your freedom, because you don't have a choice about what context length you train on. The scaling laws tell you, and you have to train at the context length that will minimize your loss. So the real issue here is that the scaling laws say you should be training on a short context. Why do we think that's the case? It's the architecture. The transformer architecture, with its quadratic dependence on context, just means that the costs of increasing the context length are way too high, and the benefits just do not balance out. Which brings us to the way that context lengths are going to get longer, and it's with the next generation of architectures beyond transformers, into what people often call sub-quadratic architectures. The reason is, as we discussed before, the transformer has a growing state. In fact, it's a linearly growing state size. The KV cache is the size of the number of tokens you fed into it, which means the overall cost of processing a sequence is quadratic. But if you instead have a fixed state size, the cost is the state size is constant, then the overall cost is just linear. And sub-quadratic just means anywhere on this spectrum. Obviously, the closer you are to a linear cost, the more efficient you'll be at long context. Now, you should be a little bit suspicious of this if you've been in the field for a while, because LSTMs did this, RNNs did this, and the transformer replaced LSTMs. So what's the point of bringing this up if it just performs so much worse? And while this was true maybe 5 years ago, actually, there has been a huge amount of work on what I call modern sub-quadratic architectures. We're well beyond the LSTM. A couple of the important changes now. All of these architectures are very efficient at exploiting the hardware. The LSTM was a fundamentally recurrent process to train, and GPUs are very parallelism heavy. So you actually need to set up a different sort of architecture in order to exploit the GPU. And these do while also retaining the linear cost of an RNN. Another big improvement is just taking architectural ideas from transformers and related architectures, understanding that the focus needs to be on scaling laws and just figuring out how to get that right. They are already crushing transformers in some domains where context plays a big role. For example, DNA sequence modeling. And the progress is really exciting. A lot of people working on this, and every month we get closer and closer to concretely usurping transformers on their own turf of large-scale natural language modeling. Some work that I'm most excited about is this is stuff that I work on at Manifest AI. We're a small research lab focused on pushing the architectural and algorithmic frontiers that enable us to train at long context. Recently, we open sourced what we call power attention. This is a key central piece of a family of sub-quadratic architectures called linear transformers. And the most crucial aspect of what we bring to the table here is that rather than having a fixed size state that is also inflexible across problem difficulties, we have the ability to, in a very efficient way, by exploiting some cool mathematics called the symmetric power, decide how large we want our fixed state size to be and tune it to various problems. This means that as you scale up the state size, you can wind up with a model that dominates transformers at all different scales, at least in the flops. In terms of real wall clock wins, we're also extremely close. You can see that in the plot at the left. In the middle is the comparison between where we're at in the theoretical and empirical performance. Our models are fast. We have a high-quality CUDA implementation of these mathematical ideas that lets you actually run them wall clock speeds as fast, or in some scales even faster than a transformer, and get this remarkable performance. So it's all open source as of this week, actually, and we've got a growing community of people excited to be working on these problems. So if you're interested in training models or doing inference without the obnoxious KV caches following you around everywhere, hit us up. We've got a Discord, and so with that, I'm just going to make some quick, bold predictions here. The writing is on the wall for me as somebody working in this space. Transformers do not have a lot of time left as the dominant architecture. By the end of 2025, this year, every hyperscaler will at the very least be working on a sub-quadratic foundation model. By the end of next year, nobody will be using transformer models, or almost nobody. And by the end of 2027, it will be getting all the goodies that I discussed at the beginning of the talk, including, and I'm going to come back to this now, the beginning of a transition from centralized to decentralized AI. So I want to talk a bit about what the picture of centralized versus decentralized AI looks like and how the context scaling regime is going to influence it. Hyperscalers, you can picture it like this. They got a lot of compute, they got a lot of data, and crucially, it's all in one room. Everyone else collectively has more compute and data, but it's scattered, it's fragmented. No one person has it all together. So inference, this is not a problem. Inference is in some ways an inherently distributed process. There's not a real advantage to having all of your compute in one room when you're doing inference versus broadcasting it out to a bunch of different players, assuming everyone's tech stacks are well situated. Long context puts inference on steroids. Right now, because the prompts are so short and models are barely capable of using them, everyone's copy of ChatGPT or Claude is basically the same. They have more or less the same capabilities. You can do a little bit of improvement. You can influence it a little bit by putting some good stuff in the prompt, but it just can't go very far. If you imagine what a true long context model would look like, it's a completely different picture. It goes from being sort of the consultant who shows up and tries to be helpful to the college new grad who you hire and train and work with for an entire career as they proceed up the engineering stack until they know everything about the company. That's the promise of long context models and something that we don't currently see. It means that once we are able to truly process long context in this way, you could genuinely have a state-of-the-art AI for some task simply because you gave it the correct information in order to help it do that task. And that takes a lot of power away from the centralized hyperscalers who wouldn't have, unless you release it, that same prompting strategy, one could say. But of course, you're still reliant in that scenario on the hyperscaler for the underlying model. So what about training? Training, unlike inference, you do have a big advantage from having all of your compute in one room, and that comes from the communication bandwidth. This is fundamentally the reason why distributed training is extremely, extremely hard. It's because training a large-scale model requires a huge amount of communication between the GPUs. So the two parts of training, computation, communication. Computation is you're given a document or a data set or a mini batch, and you compute a gradient, and communication is you send that gradient to other GPUs. Now, if these are the same order of magnitude of time, they can be overlapped, and there's actually almost no downtime for the GPUs themselves. But if the ratio is poor, communication can easily become the bottleneck, and this is the situation we find ourselves in when we're trying to envision what a decentralized training process would look like. So given that we're in this situation, how might we get out of it? One thing you could think of, what if you increase the model size? This does mean you're doing more computational work per gradient update, but it also means you're sending around a much larger gradient. So the ratio is actually unchanged, and this doesn't help you. All right, let's try something else. What if we increase the batch size? Well, this does help. You're doing more work per GPU before communicating the gradient, which is the average of the gradients across the batches, so it's not larger to do a gradient that was computed across more batches. However, you can only get a little bit of juice out of this because the improvements that you get in the gradient quality from increasing the batch size decrease pretty quickly as you scale up that batch size. It converges quick. Which brings me to, of course, long context. If you increase the context size, you are required to be doing, because of how backpropagation works, more work per device, which means that the communication time relative to the amount of time spent computing each update goes way, way down. And in a world where we are regularly training models using context sizes of not just million, but billion or even trillion tokens long, that means that each GPU is doing probably a huge amount of work before communicating. And in this case, sending a big set of weights across the Atlantic doesn't seem so bad anymore. So essentially, I think if there's one takeaway from this talk, it's going to be that context is going to be huge. If there's two takeaways, it's that context is going to be huge, and power attention is hopefully going to be the path to get there. So if anyone is training these models and interested in training them faster, more efficiently, and at larger context, or if you're working on long context problems like DNA modeling, likely financial modeling falls in this bucket, or similar, link is there. And I also want a big shout out to my co-founder, Carlos, and to the rest of the Manifest AI team for helping this happen. So thank you, guys.
Thank you so much, Jacob. Kader, do we have time for some questions? Okay, we'll have to, I want to allow, let's do a couple questions because I want to let people ask a couple. We have time for a couple questions here. Yeah, please? No, take the mic right there, yeah.
Yeah, just a question about data availability. Isn't there a limitation on the amount of long context data that we have?
Yeah, that's a great question. So right now, we're chopping up the data way more than we have to, is the short answer. For example, take Twitter. Imagine you're training on a Twitter data set. Okay, each data point is 270 characters long. But that's not the only temporal or sequential structure that exists in Twitter data. You could instead imagine training on each user as a data point, all tweets they've ever produced. Now suddenly, the data points are getting longer. Now imagine training on all of Twitter as a single sequential stream. Billions and billions and billions of tokens long, all data ever produced by anyone on Twitter in one document. This is real long context data. And the reason nobody does this is because it's too expensive to do so, and nobody wants to train on data at those contexts.
But isn't it also that those data points are kind of disconnected? Like they're not, if you train on all of Twitter together in one sample, like those tweets are not necessarily related.
There's absolutely sequential structure. For example, this week, everyone was talking about the inauguration. Tweets earlier in the week would be predictive of tweets later in the week. And this sequential structure is also, over the decades, the general interests of the population have waxed and waned. This sequential structure is there. It's exploitable. We just don't, because we don't tend to train at that context length. And this applies not just to Twitter data, but to all sorts of data, where if you really squint at it, for example, news articles is another one. Okay, maybe all news articles from a particular author or on a particular topic or from a particular publication influence each other and are predictive of each other, and it's worth concatenating them into a single long sequence before beginning training.
Thank you.
How does this relate to Google's recent paper of the Titans? So this is the sort of thinking of context as your short-term memory, and you're saying, let's make that longer and longer, put everything there. They're looking at other forms of memory, like working memory and long-term memory for models, and combining the sort of linear approach and the transformer approach.
Yeah, there's a couple things to that paper. One of them is the hybrid models. That falls under the sub-quadratic bucket as something that has some quadratic aspects and some linear aspects, so it averages out to just be sub-quadratic. Well, not exactly, but basically. Titan specifically is also doing some very interesting work. One perspective on the linear transformer architecture that I mentioned as our main focus is that it's like the network itself is doing gradient descent against a very specific target at each step of inference. So there's gradient descent on the weights that happens at train time, and an interpretation of gradient descent on the state that happens at inference time. And there's a lot of interesting mathematics to explore in that sort of like corner of idea space. And Titans is one of the latest, most interesting works in that regard. So yeah, really good stuff.
Okay. What do you think is the main reason for the needle in the haystack problem with long context, and how is sub-quadratic architecture going to resolve it or maybe make it better?
The needle in a haystack as a benchmark is very commonly used, right? You take a bunch of, I think it's usually Paul Graham essays, and then one sentence with a number in it, and after reading the whole long sequence, you have to regurgitate the number. In general, this is a problem that I think all architectures, quadratic or not, are well equipped to solve. When you think about what it means to have a fixed state size versus a growing state size like a transformer has, what that means is you cannot memorize everything. That means, of course, you have to compress the information that you see into your fixed state size in order to make the most optimal predictions. Right. I believe this is a much better analogy for how humans work than a transformer, because humans are constantly, we have a fixed cranial state size, and we're constantly compressing our daily lives into it. We don't have photographic memory and immediately recall everything we've ever seen in our entire lives just to decide, which coffee we want that morning. That'd be way too expensive. Needle in a haystack for a fixed state size model, you can just imagine it's reading through the text, immediately discarding almost everything that it sees. It encounters the needle, it stores that in its state, and then it continues reading until the end of the prompt, and then regurgitates the thing. Now, if your needle is really big in some sense, too big to fit in your state size, now we've got a problem. Now there's actually no way to do that. And that's why our research focuses on efficiently expanding and contracting the state size in a problem-dependent way. So just like we adjust our architecture based on our compute budget, we want more or less parameters. In this case, we're also going to be adjusting our state size based on the compute budget. We can have a larger or smaller state depending on how difficult the problem we're trying to tackle is and what our budget is.
Okay, but I mean, sorry, I can talk later, but if you still have a long context and the needle is still small, how does shrinking the state size actually
the smaller the state size is, the faster you can be per step. Having a larger state, you're basically paying something per step. And transformers have the largest possible state size at every step. You're paying the maximum amount at every step, which is why they're so unscalable along the context axis. But when you have a fixed state size, you can make, if you know that your needle is going to be very small, you can make that state really tiny. You're paying very little per step, and so you can handle extremely long context in a very cost-efficient way while still getting the same performance. Okay. You remembered the needle, after all, right? That you just needed that one piece of information.
Sweet. Thank you.
Thank you.
Thank you so much, Jacob.